Here's the search problem. Before a single line of code, there's a question nobody's answering. Where do you actually go find domain data good enough to build a clinical reasoning model on? Not, I already had this data set lying around. Actually go and find it the way you'd have to if you were doing this yourself, right now for the first time. That's what this video is, not, here's what I picked. Here's how you'd go pick it. What a dataset card actually needs to tell you. When I land on a candidate dataset on Hugging Face, there are 6 things I need to be answered before I download a single byte of it. License. Is this actually usable, or is it research only with vague distribution terms that turn into a legal problem the moment I publish a model trained on it? Real versus synthetic. Real teaches the model authentic domain language. Synthetic text teaches whatever the generating model's own style happened to be. I need to know which one I'm getting into so I don't fool myself about what the model will actually learn to sound like. Scale. Is there enough volume that I can run multiple specialized generation passes without recycling the same 500 documents 5 different ways? Format and schema. Am I getting the title and abstract, full text, or structured fields? Because that determines what kind of training signal is even possible. Known quality issues. The discussion tab and any linked papers usually already have someone complaining about duplicates or encoding problems, and that's free due diligence I'd be an idiot to skip. And finally, task fit. Does this data structurally support the reasoning behavior I actually want to teach, or am I forcing a square peg into a round hole because the data set happened to be convenient? Finding a data set is easy. Deciding if it's actually good enough and being honest about where it falls short is the part people skip. A real evaluation isn't a list of reasons something is great. It's a list of reasons it's great right next to a list of reasons it isn't, and a decision about whether the good outweighs the bad for that specific job you need done. So let's do that out loud for both of these. So one of the best ways to search for your data sets is by using your favorite AI, whichever it is. I like to use Grok. I'm going to say, look on Hugging Face for cancer and oncology data sets we can use to make training data for tuning a LLM. Let's see what it gets back. So as we can see, the top recommendations are the CyberPsych PubMed Cancer NLP textual data set that I'm already using. That's why I used it, because I went through this to find it. And then it shows some other ones in here, including the Microsoft CancerGUIDE, which I'm also using. So this helps filter out through all the results that you wouldn't want, like animal testing, or I can't even think of any other ones right now, but if you were to go search directly on Hugging Face, you would say cancer data set. And you see in the data sets list here, you'll have choices, human-based AI, refined. Let's take a look at this one. Refined TCGA PRAD prostate cancer pathology data set. So this is just on prostate cancer. So this is very limiting. So let's try using PubMed cancer. And you see the data sets came through for what we're using, the CyberPsych one, and it showed up at the top. And if there's multiple, you'll see a link here that says see 7 data sets results for PubMed cancer. It'll say whatever number there is that it comes up with. So let's take a look at all 7. So some are older. CyberPsych was made in December 1st, 2024, but cancer is cancer. So for our purposes, this was a good result set to use. So whatever you're looking for, like let's say you're looking for stoicism. There's 4 data sets for stoicism. You'd look through these, try and get an idea of what's inside of them. These are question and answer pairs. For Marcus Aurelius, Seneca, and Epictetus. So another way of doing this would be to go and actually get the books. And a free site to go and get the books is the Gutenberg project. Library of 79,000 free books. So you can go in here to get the books, and then you can use scripting to extract out the information from the books as well. Let's look up Epictetus. Yep, here's books by Epictetus. List by authors, pick the exact author, click on the book, then you can download the book. And always look for the license if there is one. Usually these are all out of license because these are ancient, but you want to make sure of that. So you can download plain text. Here we go. Let's get the plain text. No cost, no restrictions whatsoever. You may copy it, give it away, reuse it on the terms of the Project Gutenberg license included in this ebook. So this is a lot more cleaning you'd have to do to scrape out all this, scrape out the contents, scrape out the notes, scrape out the introduction, bibliography. And then here's the actual book. And here's where you'd want to extract this actual content here and use that in the later notebooks to generate the question and answer pairs. You want to scrape out the footnotes. You want to scrape out all these other references, and then the license as well, because that's going to be the clutter that I was speaking about earlier. So you want the good content from the beginning of the book to the end of the book, and work on that in the next video. The PubMed Cancer NLP dataset is real scientific literature, roughly 100,000 title and abstract pairs across 10 major cancer types. Not synthetic, not paraphrased, actual abstracts written by actual researchers. That matters because the language in these abstracts is rich in exactly the material I need. Mechanistic detail, biomarkers, trial results, study limitations. That's the raw vocabulary and reasoning texture of the oncology literature, and there's no substitute for the real thing when the goal is teaching a model to sound like it actually reads this material. But I'm not going to pretend it's clean or complete. It's noisy, HTML entities, inconsistent Unicode, retracted papers, near duplicates, short, low-quality stubs, all present in real volume. It's abstract only, no full text, so there's a ceiling on how deep any single question can go. And critically, it has zero patient-level decision context. It teaches a model to reason about literature. It does not teach a model to look at one specific patient and decide what to do about them. That gap is real, and is the whole reason the second data text exists. What if variance? A different comorbidity, a different age of performance status, a new mutation, a different prior treatment history. The honest weaknesses is synthetic, not real patients. It's small, 316 cases total, nowhere near PubMed's volume. Its demographic and clinical diversity is limited compared to what you'd see in real-world case volume, and it demands careful prompting so the model never drifts into sounding like it's issuing unqualified treatment advice. Here's the actual thesis of this whole video. PubMed without CancerGUIDE gives you a strong literature reasoner that's genuinely weak at individual patient decisions. CancerGUIDE without PubMed gives you a confident decision maker that has no real grounding in the evidence base underneath its decisions. Neither one by itself produces the thing I actually want. Together, they cover the two cognitive modes on oncology-focused assistant actually needs: the ability to work carefully with the scientific literature and the ability to reason through an individual patient's presentation. That's the foundation this entire project sits on. Everything from here forward, cleaning, chunking, synthetic question generation, anti-hallucination signals, final assembly, exists to turn these two very different raw materials into training data for one coherent, evidence-bounded reasoning model. Deciding what to use is only half the job. The other half is turning 100,000 messy raw records into something actually trustworthy enough to train on. That's the next video, inside the cleaning script itself. This is the section almost no data gen video includes, and it's the one I actually care most about getting right, because a cleaning script isn't just what it does, it's also a set of deliberate decisions about what it deliberately doesn't do yet. I did not implement semantic or fuzzy deduplication, only exact match fingerprinting after aggressive normalization runs here, which means a paraphrased near duplicate slips through untouched. Catching that needs embeddings, a similarity threshold, and a much slower comparison step. A real project for later, not a blocker for making this dataset usable now. I did not implement a metadata-based retraction lookup against the PubMed or retraction watch APIs. The raw Hugging Face source has a PMID column right next to the title and abstract, but the cleaning strip's record building steps never carries that column through to the clean output. So a real API lookup by the PMID isn't wired up today. That's a straightforward fix for a later version, not a limitation of the source data. I want to be completely upfront about what this is and isn't. This is not the PubMed publication type filter. It's not a retraction watch database lookup. It's a pattern match against the title and abstract text itself, built by actually reading real records that announce their own retraction in the text. Because that's what happens more often than you'd expect in a raw text dump like this one. It's a defensive safety net, and it catches the obvious cases. Here's what's left out on purpose, and it's worth being precise about why. The raw Hugging Face source does include a PMID column right alongside title, abstract, and cancer type, but the cleaning script's record building step never carries that column through into the clean output. It only keeps title, abstract, the combined passage, and cancer type. The IDs would be noise. So live verification against the PubMed or Retraction Watch API using real PMIDs isn't wired up here. Not because the identifier is missing from the source, but because the pipeline simply drops it before it ever reaches that stage. That's a straightforward fix for a future version, not a limitation of the underlying data. Real Hugging Face dumps are not clean. HTML entities, inconsistent Unicode, retracted papers, near duplicates, stubs, non-English text, all of it shows up in real volume the moment you actually look. Cleaning this once thoroughly and writing typed, resumable per cancer type files is the foundation everything downstream depends on. Chunking, question generation, grounding checks, continuation data, DPO pairs. If this stage is sloppy, every stage after it inherits broken sentence boundaries, wasted API spend, and a model that ends up learning noise instead of clinical language. This script is about 250 lines of Python, and every one of the decisions in it was made on purpose. Let's open it. Hugging Face dataset schemas aren't guaranteed stable. A maintainer can rename or reorder a column with zero warning. This substring matches on likely field names instead of hard-coding exact column names and falls back to unknown for cancer type if nothing matches. Deliberately narrow, not a general purpose schema inferencer, just enough robustness for the one data set this targets. Filter order, cheapest and most conclusive first. Every record runs through 5 checks in this exact order. Normalize, then length filters, then retraction detection, then an English language heuristic, then fingerprint deduplication. That order isn't arbitrary. A length check is a single function call, and it disqualifies the largest chunk of junk before the script ever spends a CPU cycle on a regex extraction scan or a character set analysis. Everything that survives an earlier filter is one less record the more expensive filters ever have to touch. At 100,000 rows, that's not a runtime emergency, but it's a habit worth having at any scale. And it makes the drop reason accounting honest. because a record gets attributed to the first real problem found, not every problem it happens to have. Why 200 characters and why it's not a flag? Segment 7. Abstracts under about 200 characters are almost always low value or broken. A title copy-pasted into the abstract field, a see full text stub, an incomplete record, an errata notice. 200 characters kills most of that while keeping legitimate short clinical abstracts intact. Below that line, there's simply not enough material for sentence-aware chunking or question generation to do anything useful with. And I want to point out something small but deliberate. This threshold, along with the 10-character title minimum and the 15,000-character abstract cap, is a hard-coded constant in the script, not a command line flag. That's on purpose. These numbers were tuned once by manually reading samples on either side of the cutoff. They're not meant to be knobs someone reruns 10 different ways per experiment. If they ever need to change, the right workflow is editing the constant and rerunning the whole pipeline, not a flag that quietly produces a different shaped data set every time someone forgets what value they last used. Fingerprint deduplication. This is content-based deduplication, not ID-based. Two records with the same abstract but slightly different titles, extra spaces, or different quote characters collapse to the same fingerprint and get dropped. That's a meaningfully stronger approach than trusting whatever ID field the source happens to provide. But I want to be direct about its limit. This only catches exact matches after aggressive normalization. A paraphrased near duplicate, a review paper that repeats an earlier abstract's finding in other words, will not be caught here. Catching that requires embedding-based semantic similarity, a second model, a similarity threshold to tune, and a much slower comparison than a hash set lookup. That's a real deliberate trade-off. The fingerprint hash clears out the cheap, high-confidence duplicates. Semantic near duplication is a version 2 problem, not a blocker for getting this dataset usable now.